Greetings, aspiring scientists. Welcome to my video today on polarity, bond polarity, and molecular polarity. So this is an extension into covalent bonding, following my previous videos on Lewis structures. So if you haven't watched those, I'd recommend you do. Anyway, let's get into it. So we'll go to my slides here. So this is 2.2.5 in the IB curriculum, IB-SL chemistry. Bond polarity we'll start with. So what we're going to get into today is the idea of polarity. Let me just describe quickly what that means. Polarity refers to whether there is an imbalance of electric charge within the molecular structure, whether there are a higher concentration of electrons or a lack of electrons in certain regions of a bond or molecule compared to other regions. If there is an imbalance in that structure, in the zones where electrons can be in that structure, then we have a polar bond or molecule. But if there is a perfect balance or near perfect balance, we generally consider it non-polar. And that would mean all the regions basically have the same electron density, the same amount of charge. Okay, so 2.2.5, bond polarity. So polar covalent bonds, we've defined this a couple times in my previous videos to do with electronegativity, but defining it again here. Compounds that have a bond with significant electronegativity difference will have regions of partial positive and negative charge. So the atom with more electronegativity on the Pauling scale, in this case I have an example of HF, hydrogen fluoride. F has much higher electronegativity at 4, H is lower, around the middle of the scale, like 1.5 or 2 or something like that. So fluorine pulls the electron pair much closer. That means in this bond, fluorine has more electron density, and that region, F, has more negative charge. And since it took those electrons from the H region of this molecule, of this bond, that region has a positive partial charge. Okay, we're not really dealing with full charges here. They're called partial charges, and they're written with the Greek letter delta, small delta. And we can draw this with an arrow that has sort of a cross on one end. That's the way I usually draw it and the way I usually see it in textbooks. And we usually point the arrowhead towards the negative side. So arrow, cross arrow, pointing towards the negative region F, delta negative there, and then delta positive near the cross. So this is one bond, but in this molecule it's just a linear molecule with one bond, so this also represents the molecular polarity of HF. Okay, so this bond is negative towards H, and this molecule is it's negative towards F, and this molecule is negative towards F as well. But we'll see when there's multiple bonds in a molecule, you have to look at each one and consider the whole picture afterwards. Okay, what about non-polar covalent bonds or pure covalent bonds? So this often happens when you have two of the same atom bonded together, like in a diatomic gas, maybe Cl2 for example here. This is what I'm showing. Their electronegativities are 3.16 each, so the difference between that is 0. That means each one cannot physically pull any more electron density than the other one. They share it completely. And so there's no region in this molecule that has more negative or positive charge. Pretty simple compared to polar molecules, I think. Alright, so one thing we need to get into is the idea that a dipole or a dipole moment. This is the actual physical representation of polarity in a bond. Dipole moments are vector quantities. Okay, if you've ever studied physics or math in some detail, you might have heard of vectors before. But for those of you who haven't, it's not really needed that much in the IB chemistry curriculum, but I'm going to go a little bit deeper into it than we need to, just to further our understanding. So there are two types of quantities, scalar quantities and vector quantities in our universe that we as humans can measure. So what's the difference? Well, first let's define scalars. These are quantities that have a value or a magnitude or a size associated with them, but they do not have a specific direction. So you can think of things like energy or time. Time you could kind of think has a direction forward and backward, but generally we don't consider it to have a vector direction. Other things, volume, mass, these do not have directions either. They're just a property of something where you can measure the size of that by the magnitude, the size of the number. 10 grams is higher than 5 grams, or 20 joules is more than 10 joules. But there's no particular direction to these quantities. Okay, so scalar is kind of the easy thing. It follows all the mathematics that you would follow for just normal numbers. So vectors that we're going to get into do have direction. And we need to define direction in a little bit of detail. So directions are ways that we can orient ourselves in one-dimensional, two-dimensional, three-dimensional, four-dimensional, and so on kinds of space. So you guys might know one dimension is like on a line. You can go forward or backward. Two-dimensional is like a plane. A plane, you have multiple directions. You have an X and a Y axis on a Cartesian plane graph, for example. 3D, you're getting into 3D, which is really a good representation of our universe, our world here. So a lot of physics and chemistry does deal with 3D. But in IB high school level, we actually often only deal with 2 dimensions. In physics anyway. In chemistry that we have seen, we've been dealing with a couple 3-dimensional molecular structures, molecular 3D Lewis structures, for example. Geometries, we called them. So they might come up for sure. We're not really going to talk about 4-dimensional or higher space, though. So we can use degrees, like, 20 degrees, 90 degrees, 180 degrees around the circle. Cardinal directions, northeast, southwest, those kind of things in the middle also count as cardinal direction notation. Polar coordinates, these are a way to orient in 3D space. I talked about that a little bit in my video about the Schrodinger equation. It uses polar coordinates, I believe. So you can use 2 angles and 1 distance or 1 radius to show a direction in 3D space, rather than 3 component vector directions. Like I can say, go forward a few meters, go left a few meters, go up a few meters, and the point that those 3 component vectors end at will produce 1 net direction. I think that's the way most of us think, especially if you studied math a little bit, but polar coordinates are another way. You can have 1 angle left and right, 1 angle up and down, and then a distance that will also give you a particular direction in 3D space. And then finally, radians. This is an alternate to degrees that often is better because it has no units. It's really a fundamental mathematical angle around the circle that we can use. So for now, I just want you to be aware that all of these are particular ways of measuring and expressing direction. So vector quantities. Vector quantities have magnitude and a direction associated with them. Both are equally important and necessary. Many physical quantities do have vector and scalar versions, actually. So if you study physics, you know force in newtons, kilogram, meter per second squared units. These have units of newtons, and it is a vector quantity. So you can't just say you applied a force of some magnitude, 5 or 10 newtons or whatever. You need to also indicate what direction that force is occurring or what direction it's applied in. Is it forward or backward or at an angle, up or down? This matters hugely to what happens and how we model things happening in our universe. What else? Velocity. This is kind of what you might think of as speed, but it really is attached to the direction. So you can have, meters per second or kilometers per hour, but a velocity must have a direction as well. Forward, backward, up, down, some angle, whatever. acceleration. You probably are familiar with this as well. This is a change in velocity. So if you go from 5 meters per second to 10 meters per second, you've accelerated along the same direction that the object was moving, right? At least some component of the acceleration was in the same direction. So you can see I've got some arrows here. We often use arrows to represent vectors because we can draw arrows in a particular direction where the arrow head indicates the direction of the quantity. And then the size or the length of the arrow is often scaled to show the magnitude of that quantity as well. So you can see I've got 5, 8, and 9.8. 9.8 being the largest magnitude there has the longest arrow. Okay, so all of these I tried to scale on the same scale, even though they're different units of measurement, just to show you. So what does this have to do with bond polarity? Well, I just want to show you there are pairs of scalar and vector quantities. The scalar version is speed, vector version of that is velocity, distance, scalar version, vector version, displacement, scalar mass, vector. There's no real vector version of mass, but there are things that incorporate mass that have vector versions like force and acceleration. Area, you might not think of area as having a direction, but mathematicians and physicists have figured out a way to get a vector or a direction out of area, which is if you take some line perpendicular to the surface, 90 degrees to the surface, what direction does it point? So there's vector version of area as far as I know. Inertia, momentum, and then at the bottom here I have dipole moment. So dipole moment that we're studying with dipoles here in bonds and molecules is also a vector quantity. So it must have a direction and a magnitude, a size. Now, we can do mathematical operations with vector quantities as well as scalar quantities. So to add vectors graphically, this is what we're going to be doing in chemistry here by drawing. They must be drawn on the same scale, which we can generally do. We're going to take the size of the electronegativity difference, I think, the size of the dipole moment to be the size of our vector arrow, and then the direction is the direction that the bond exists. So draw the first vector, then at the point when it finishes, start drawing the next vector, keeping its original direction. The new resultant vector can be drawn from the starting point of the first vector to the end point of the added vector. Okay, this is really important. So imagine that you've seen two bonds in your molecule. You've got V1 and V2, as I've drawn here on the left. Well, the resulting dipole moment in your molecule is going to be V1 plus V2. It's all the vectors added up, all their magnitudes and directions added up. So you need to know how to add vectors together. If you follow the rule I have here, you take one vector. It actually doesn't matter which one you start with. You draw it, and then you add the next vector. The way that you add it is that you start drawing the next vector at the end of the first vector, where its arrowhead exists, okay? So although I've got these two vectors, V1 and V2, beside each other on the left, if I want to add them together, I need to do what I'm showing here on the right, which is draw V1 or V2. And then at its arrowhead completion zone, start drawing the next one. Okay, so we're doing this. You draw V1 first. Where it finishes, you draw V2. Now you can imagine you're somebody walking along this path, okay? You walk along V1, you go in some direction for some distance, you reach the end of that path, and then you have V2. You start walking on that path at a different direction, right? V2 has a different direction, different angle around the circle. And wherever you stop, you're going to look back at the point where you started from and say, okay, what if somebody just walked from my starting position to where I am now? That's called the resultant vector. We can label this with R usually for resultant. So it's just where do you end up if you walk on a path of these two vectors? That's a good way to think about it. I'm talking about walking, but the same thing applies to dipole moments or forces or acceleration or many other vector quantities. So that resultant vector represents the net dipole or the net polarity of a molecule with multiple bonds that we're going to get into in the next section. So let's move to there. Molecular polarity. So reminder, we just talked about bond polarity. Some molecules only have one bond, so if you figure out the bond polarity, you have already figured out the molecular polarity for those. But a lot of molecules have more than one bond. You have to consider adding all the vectors together. Okay, so 2.2.6, molecular polarity. Let's see some examples of net dipoles. So dipole moments, often labeled with Greek letter mu, looks like a U with a little tail on the front. So these dipole moments have size and direction. You want to add them up and check if the result is 0. So if the result is 0, what does that mean? It means, do you end up back at the starting point? If you were to walk along these three vectors, are you standing in the same place that you started if you go along each path? So here we have AlCl3, aluminum chloride. You can calculate the electronegativity differences between these. You'll find that there is a dipole moment towards chlorine in each of the AlCl bonds. But we know the geometry of this is trigonoplanar. There's a 120 angle between these. So you could actually take each of these vectors. There's one going right, one going down to the left, and one going up to the left. Add them together graphically, just like I showed on the previous slides, and you will find that you do end up back at the starting point. You end up with a resultant vector of 0. It doesn't go anywhere, it doesn't have any angle, and so there is no resultant dipole, no net dipole. This is not a polar molecule, as drawn here. AlCl3, non-polar. No net dipole. So here's a couple of examples. Water, H2O. You can check the electronegativity difference there. You'll find oxygen is much more electronegative than hydrogen. So those arrows point towards oxygen at an angle though. So since both point down, even though one points left and one points right, those parts of the vectors cancel out. The net resultant vector though is going down. You can see that if you draw it. One down to the right, one down to the left. The resultant goes straight down. Okay, so water is a polar molecule. Very polar, in fact. It has a dipole moment measured in, I think the units are Debye, D-E-B-Y-E, with D. So this has a dipole moment of 1.85. That's the magnitude of this vector. So quite polar. What about trichloromethane underneath? CHCl3. So this has one hydrogen attached and 3 chlorines attached. Now this is where things get very difficult. This is a 3D molecule, so I can't draw it very well on the page here. But you can see that the hydrogen-carbon bond is a little bit polar negatively towards carbon in the middle. But it's very polar towards chlorines on the outside. So especially if you add up those 3 vectors at the top with chlorine, those are going to be much more of an effect on the molecule because the electronegativity difference is higher. You can almost ignore the hydrogen one because it's such a small number. It's actually not a very polar bond. I've discussed this before. Organic chemists tend to call the carbon-hydrogen bond not very polar. So focus on the chlorines and carbon bonds here. So what's happening in the sort of triangle is very similar to what happened with AlCl3. You've got one going up, one going right, one going left. The resultant there is 0. But the thing is, all 3 of these chlorines are pointing upwards a little bit. And you can see there is a net dipole just because of that. Okay, if there's a plane, see if I can draw it. If there's a plane here, try a different color. That would be flat. Each of these chlorines is pointing up a little bit, so that makes the net dipole up rather than in any direction like left or right or behind. Those are canceled out by the sort of trigonoplanar, nearly trigonoplanar arrangement of these chlorines. But each one's pointing up, so we do have a net dipole moment 1.01 pointing upwards. Okay, I get that's really hard to understand and follow, especially without having a full 3D model. We just have my 2D kind of screenshot here. Okay, what about carbon dioxide? So carbon dioxide, you'll find oxygen is much more electronegative. So the dipoles point negatively towards those oxygens, but they are perfectly on opposite sides of this linear geometry, right? So you can draw the vectors, but they will absolutely cancel out perfectly. One goes up like this strongly, but one goes down like this strongly. You end up back in the same position that you started. 0 net dipole, 0 resultant vector. You can also check ethane underneath, a little bit harder to see, but this is 2 tetrahedral carbons attached together and then 3 hydrogens on each side to fill the carbon's octets, C2H6. So there's no dipole at all formed from a carbon-carbon bond. That's a nonpolar bond. So carbon and hydrogen, as I discussed before, do have a little bit of a polar bond pointed towards the carbon. But you can add up those vectors. On the left side, you'll find you have about 3 arrows pointing like this. So if that was the only thing there was, this would be slightly polar to the right side. But on the left side, we have 3 arrows as well, perfectly opposing these 3. It's hard to see that with my screenshot here. But all of these vectors will cancel out. If you tried to add them all up, you would essentially get back to nowhere, or 0. Okay, they do all cancel out, so this is nonpolar dipole moment 0. And you'll find whenever you have carbon chains like this, could be 1, 2, 3, 4, 5, 6, when they're just connected through a bunch of single bonds, kind of in a line or a zigzagging chain like this, they're almost always nonpolar, especially if it's carbon-hydrogen bonds, which are nonpolar bonds to begin with, only slightly polar. Alright, then we get to boron trifluoride. That's essentially the same as aluminum trichloride that I had on the previous slide. You can add those 3 vectors up, but you end up with a 0 resultant vector, 0 net dipole. Okay, so I get this is very hard to understand as an introductory chemistry student. Even I don't understand it that well, and when molecules get more complicated than the ones I have on this slide, if you have longer or more complicated geometries, even I don't really know how to calculate that. I think it needs to be computationally generated. But generally on IB exams, you'll be asked more basic versions like what I have on this slide. Okay, what else do we have? So I have some other points about polarity that we need to consider, especially if you really want to get an understanding of it and go beyond the IB curriculum. So lone pairs often indicate the direction of the negative dipole. Okay, lone pairs are regions of high negative charge density. So if you happen to have a concentration of lone pairs somewhere, more in one area of the molecule than another area, that often indicates that region has more negative charge. That's the direction of the negative dipole. Okay, so for example, let's consider something like ammonia, NH3. You can draw the 3D Lewis structure of that. Maybe how do I want to do this? I'll draw one hydrogen straight line down, one out of the screen like this, one into the screen with a wedge. So you can consider the dipoles on these. All the hydrogens will be less electronegative, so we have little dipoles pointing towards the nitrogen. And then you'd want to add up those vectors together, right? But it's quite difficult to do. This is a 3D structure, so the vectors are also 3D, but I'll give it a shot. One up left that has a dashed line. I'm going to draw the arrow with a dashed line as well. And then one up right, also with a wedge. So what's the resultant vector of this? It's going to look like this. Okay, basically it's like if you walked along the path of these three arrows, one goes straight up, the other goes, into the page or, along some other plane. To the left, another goes right then. So that left and right cancel each other out. The net resultant vector just goes up. Okay, so that's one way to find the polarity of NH3 if you want to go through all the vectors. But one thing you might have noticed is that there is a little bit of a shortcut you could do. Just check where the lone pairs are. And then it doesn't even really matter what's underneath. Very likely this dipole is going to be just towards that lone pair. You'll often get the same result. All right, what other points do we have? So full electric charges have the highest effect on the formation of dipoles. So we've seen sometimes, especially in polyatomic ions, that certain atoms have negative charges on them, right? Full charges, not partial charges or dipoles, actual charges. So something like hydroxide, OH minus on the O. This has an incredibly strong negative concentration on the left, so you can also consider its dipole to be in that direction. Okay, if you've got full charges like that, positive or negative, if it was a positive one, this negative dipole would be pointed in the opposite direction. Keep that in mind. But charges have the highest effect on the formation of polar regions, or charged regions, right? Okay, what else can we say? We can often deduce polarity on fixed or frozen structures, but we need to be aware the single bonds rotate. This is an important point that is often not considered, I think, in IB chemistry and textbooks. So imagine I have something like chloroethane. So chloroethane is two carbons. Hydrogens here. Actually, let me draw it 3D. And then I've got a chlorine and a couple hydrogens here. Also 3D tetrahedral structure. So you'd probably go through the bonds in this or check where the lone pair concentration is and say that this has a dipole basically in this direction, negative, right? Towards that chlorine. and that would be true, but what you've done is frozen this structure in time and in space. You found the dipole of this frozen structure, but what you need to know is that single bonds rotate. Each single bond in this molecule is able to rotate, and the one that's really important to consider is this one in the middle. This can rotate. So instead of, 3 hydrogens on one side and then 2 hydrogens and a chlorine, what we probably have more likely over time is a cone that represents carbon-hydrogen bonds, and then a cone here as well. And this one is bigger and more negative because of that chlorine. Okay. So you can imagine it's kind of spinning around, and over time, these 3 bonds average out. And so instead of that dipole pointing up to the left, because that's where it was in the frozen structure, now that chlorine is somewhere in that cone. So on average, the dipole is most likely just straight through the center of that cone. Okay, that's probably a better representation of the dipole, right? Because sometimes the chlorine is up, sometimes it's left, sometimes it's right, sometimes it's down. But overall, on average, that cone is pointing away from the central carbon-carbon bond. So the dipole, most likely, on average, just goes straight through the center of that cone. Okay, very hard for me to draw on a 2D screen like this, but I just want you to be aware of that. These bonds rotate around and average over time. So you can't really consider this chlorine to be in any particular position in this tetrahedral structure. Rather, it's spinning around. All right, what else can we say? HL considerations. HL, we're going to study something called resonance, which is the idea that double bonds and charges and lone pairs, when they're connected in a certain way, they will also average across several locations. So resonance leads to an averaging of bonds, of charge, and lone pairs across the shared area. So often structures that might look polar at first are non-polar on average when you consider resonance. And the best example I can give is something that we've studied a lot. That's NO3-. Oops. So for NO3-, we had a double bond, we had a negative oxygen, and we had another negative oxygen and a positive nitrogen in the middle. Like this, right? So it looks like there's more negative charge, there's more lone pairs on the bottom, and since one goes left and one goes right, overall the net vector on this would just go straight down. Hopefully you can see that, considering the rules and things I just explained to you. Negative charge overall will basically determine the dipole moment of this molecule and the direction of that vector. So we've got one negative charge on the left, one on the right, but both of them will point downwards compared to that central nitrogen. So the net dipole looks like it would go down. But the idea with resonance is that I chose to put that double bond on the top. I could have easily drawn the same structure with it on the bottom right and have negative charges up and left. Right? And in this case, the dipole moment would go up left. And I could also have drawn it on the bottom left, that double bond, and have negative charges top and bottom right. If you do that, the net dipole basically goes upright, like that. So what you need to consider is the average of these 3 structures. So not only do you have to average the bonds or add the vectors up of the bonds inside one of these structures, you do that first, and then you consider all 3 possible structures that I could have drawn, and average those, add those vectors up together. And what you'll see is that looks a lot like the aluminum trichloride or the boron trihydride, whatever structures we've had before, where these vectors will just cancel out. One down, one up left, one up right, net 0. So NO3 minus is actually nonpolar when you consider what are these called resonance structures. That's an HL topic that I'm just putting in at the end of this SL video because polarity is a very difficult and nuanced topic that you need to know, even especially more in HL. Okay, so do I have a couple examples perhaps we could look at to determine whether the following molecules are polar or non-polar molecules? So hexane, I'm not going to draw every vector in this, but C6H14 is just a long chain of carbons and hydrogens, like I was discussing before. It's 6 in a row. The ones on the end have 3 hydrogens. These will be rotating around like in a cone, like I showed with chloroethane. Then you've got a couple pairs of hydrogens on these middle chain carbons. All of these will be tetrahedral, by the way. I'm just not drawing the full 3D structure wedges and dashes to save some time. But if you look at this and consider each vector, the carbon-carbon bonds have no polarity. Carbon-hydrogen bonds are the only things you need to consider. But you'll have an equal number that oppose each other. So what do I mean? We've got some going down right. For every one that goes down right, though, you'll have one that goes up right. For every one that goes down left, you'll have one that goes up right. So those cancel each other out. These cancel each other out. These cancel each other out. And the cones on the ends also cancel each other out overall. On average, this cone is going to be pointing inwards like this. This cone is going to be pointing inwards like this. They cancel each other out. So non-polar for this. Adding up all the little vectors, as I said, that's generally going to happen for carbon and hydrogen straight chains like this, or zigzag chains. Ammonia, NH3, we've just done that. We've seen it is definitely polar because there's a concentration of negative charge on the lone pair, and the geometry and the polarity of the NH bonds makes it polar. I'm not going to draw that again. I've drawn it on a previous slide. You can just go back in the video. HCN, this is a linear molecule we've seen a couple times before. So there's going to be a little bit of a dipole from H to C. And there's going to be a bigger dipole from C to N. N is more electronegative. So you can just add up this little dipole with the big one. They both go in the same direction. So on average, you just get a big dipole going to the right. I think that one's even higher dBA, a higher magnitude than water, which is pretty impressive. All right, so that is polar for sure. Fluoroethane. This is going to be exactly the same as chloroethane that I drew on a previous slide. Just chlorine switches places with fluorine. So, sorry, this one will have some rotation to make that cone shape. And you will have a net dipole through the center of that cone, like this. I believe. So this is polar as well. Okay, so do some practice. Maybe find some practice questions online. Ask some AI large language models to help you out. But generally, you don't need to do that complicated structures for IB, especially SL chemistry. Okay, hopefully you learned some things and you like my style of figuring out molecular polarity. Next time we'll get into intermolecular forces, very important for actually finding out what the properties of certain covalent bonded compounds are. All right, have a good one. See you next time. Thanks for listening. Bye-bye.